In this video lecture, I will be discussing a type of first-order differential equations called Bernoulli equations. So let me recall first the general format of a first-order differential equation. So we have something like this. Derivative dy dx equals to a function of x and y. That is the general format of first-order differential equation. Here, y is the unknown and x is the independent variable. And of course, dy dx may also be written as y prime. We have seen two types of differential equation like this. Separable equation. Separable equations are equations that we can factor the right-hand side into something like g of x times h of y. So the right-hand side can be factored completely into a function of x alone times the function of y alone. That is called a separable equation. And another type that we have learned in the previous lectures is linear equation. So linear equations are not separable equations, but they can be written in the form, this is called the standard form, dy dx plus px times y equals to qx. Now, you should have recalled from the previous lectures, depending on the type of the equations, we have different methods to solve. So for linear equations, we need to use integrating factor. For separable equation, we have to separate x on one side and y on the other side. Now, for this topic, we have Bernoulli equation. Bernoulli equations look similar to linear equations, but of course, they're different. And we need to follow the method for Bernoulli equations to solve them. Bernoulli equations are equations that can be written in this form: dy dx plus bx y equal to cx times y to the power n for n different from 0 and 1. Now, if you compare Bernoulli equations and linear equations above, you see that they are very similar, especially the left-hand side are the same format, because we have derivative plus a coefficient times y. The right-hand side for linear equation, we have qx alone. But for Bernoulli equation, instead of the coefficient in x alone, we do have a factor y to the power n. And because of this, Bernoulli equations are non-linear equations, and we need to use a different method to do. The condition that n different from 0 is to make sure that we do have y to the n. Otherwise, y to the 0 would be just 1. And then n shouldn't be 1, because if n were 1, then we just have cx times y, which we can combine with bx times y here. So how do we solve such a differential equation? So what we will do is we make it look similar to linear equation by getting rid of y to the n. We're gonna multiply through by y to the negative n. Doing so will make the right hand side become the c of x, y to the n will be gone. But we will have on the left hand side y to the negative n times dy dx plus bx y to the negative n y here, and then cx on the right hand side. The middle terms here can be combined into a new exponent of y to the 1 minus n. And the next step is to use something like substitution. Is it called substitution in the sense that instead of the original unknown y, we're gonna introduce new unknown denoted by v here. And this unknown is nothing but the exponent of y, the power of y that we have obtained in the previous step. By introducing the new unknown v, we will have a new equation, a linear equation in v. We then solve for v, and from there we solve for y. So let's go to the examples and see what the procedure looks like. Example 1, solve the equation. And I have y prime equals to 2y plus 5e to the x y cubed. For this problem, I have an initial condition. As usual, the first one is the ODE, ordinary differential equations. The second is initial condition. And what it says is when x equal to 0, y equal to negative a half. Okay, that the two components of the problem. So first, we solve the ODE. Let's rewrite the equation in the format y prime plus bx y plus cx y to the n. Very similar to linear equations. So the equation will be written as y prime. We need to bring the 2y to the other side. We have minus 2y, and then we have 5e to the x y cubed on the right hand side. And this matches the format. The next, we will try to get rid of the factor y cubed here by multiply through by y to the negative 3. Doing so, the left hand side, we have y to the negative 3 y prime, and then minus 2 y to the negative 3, and we have a factor y already there. On the right hand side, we don't have any y. And simplify the middle factor. We have y cubed, y to the negative 2 times y becomes y to the negative 2 equal to 5e to x right hand side. Now we introduce new variable, introduce new unknown v, and v is just whatever powers of y we have received in the previous step. So y to the negative 2 here. Now we need to take the derivative of v. Note that the independent variable for this problem is x. That's what we are taking the derivative, what is pegged to. So we take the derivative of v, will be dv dx. And you need to be careful to use the chain rule here. Dv dx is dv dy times dy dx from calculus 1. Right? And what is dv dy? dv dy, v is 2 to negative 2. So dv dy, derivative with respect to y will be minus 2 and then y to the minus 3. But don't forget, we need to multiply by dy dx, which from the chain rule. By using the Gram rotation, this can be rewritten as minus 2 y to the negative 3, and then dy dx is nothing but y prime. This is dv dx. So you see that after taking the derivative of v, we have something that appears in the equation here. Y to the negative 3 times y prime. But we have a constant negative 2 in front. Let's divide that. Let's get rid of that constant by dividing everything by minus 2. Then we will have on the left say minus a half dv dx equal to y to the negative 3 y prime. Okay, so now we're gonna plug into the equation. So what do I mean by that? Whenever we see y to the negative 3 y prime, we should replace by this minus a half dv dx. And then whenever we see y to the negative 2, we should replace by v. And our original equation is right here. So we have first y to the negative 3 y prime. That y to the negative 3 y prime should be replaced by minus a half dv dx. And in the middle, we have minus 2 y to the negative 2. But y to the negative 2 is v, so we get minus 2v. On the right hand side, we don't need to do anything. It's just phi e to the x stay the same, phi e to the x. So we have a new equation in the new unknown v, and this equation is a linear equation. It matches the format of linear equation. Linear equation. But not standard form yet. So to get the standard form, we have to make this coefficient 1, right? So we multiply through by negative 2. Multiply through by negative 2. So we getting rid of the first coefficient to get dv dx, multiply the middle term by -2, we get plus 4v, and then on the right hand side we get minus 10 e to the x. So now we have, oh, so I don't know what happened here. This is not what, yeah. So now we have a linear equation in the correct format, in the standard form, but the unknown is v. Let me rewrite linear equation in v. So it should be of this form: derivative and px v. On this side we have qx. So px is 4 and qx is minus 10 e to the x. Now this is in the previous topic, so you should be able to solve for v from here. You might pause the video and try to solve for yourself. So we continue solving the linear equation by using integrating factor mu x is e to the integral of px, which is 4x dx. So we have e to the 4x. And as usual, we don't add a constant c for this step. Once we know the integrating factor, we multiply standard form through by e to the 4x. The standard form is right here. We need to multiply through by e to the 4x. So the left hand side becomes e to the 4x dv dx plus 4e to the 4x v equal to minus 10 e to the 4x, and then we also have e to the x already there, right here. Now, as before, for linear equation, the left hand side is the derivative of product. And now v times integrating factor e to the 4x. And as usual, we should double check that it's actually product rules applied correctly. And then on the right hand side, we combine the two, e to the 4x and e to the x becomes e to the 5x using the rules of exponential. Now integrate v e to the 4x equal to the integral of minus 10 e to the 5x dx. So what do we get? We get minus 10 e to the 5x over 5. And now at this step, we should add c. So the left hand side v e to the 4x. Okay, so simplify, we have minus 2 here, e to the 5x plus c. Now, we do have initial condition, which says that when x equals 0, y equal to minus a half. But instead of having y, we have v, right? So before continuing, let us replace v by e to the negative, by y to the negative 2, because the goal is to solve for y. The v here is y to the negative 2, which means 1 over y squared e to the 4x equal to minus 2e to the 5x plus c. And now we may use initial condition, which says that x equals 0, y equal to minus a half. We plug these values, we have 1 over y squared minus a half squared, and then e to the 0 minus 2 here, e to the 0 plus c. Simplifying this, on the left side we have 4, on this side we have minus 2 plus c, and so we get c equal to 6. And as before, once we know c, we plug c equals 6 back into the equation here, denoted by star. What we get is e to the 4x over y squared equal to minus 2e to the 5x plus 6 here. Now we need to solve for y. So how to do that? We could, because here we have e to 2 of 4x, so we could multiply both sides by e to the negative 4x to get this 1 over y squared on the left hand side. Okay, so what I'm doing here is multiply through by e to the negative, and we need to distribute in there, distribute in here and distribute in there. We get minus 2 e to the 5x times e to the negative 4x will give us e to the x plus 6 e to the negative 4x. Then we need to take reciprocal everything, which 1 over y squared divided by minus 2 e to the x plus 6 e to the minus 4x. And we need to take square root to solve for y. There's something going on with my pen here. Okay, y square root. So how do we, when we take square root, don't forget to have plus or minus. However, we need to square root e to x plus 6 e to the minus 4x. That's the first square root. Or another square root with the minus sign. Minus 2 e to the x, 6 e to the minus 4x. But that the plus side is not correct solution. This is not correct. Why is that? Because initial condition says that when x equals 0, y equal to minus a half. So there's a minus side in the value for y here. So the plus is not the correct one. The correct one is the minus square root. Okay. So I'll just write out the answer. The final answer correctly is y is minus square root of 1 over minus 2 e to the x plus 6 e to the minus 2x. This is the solution to the given initial value problem. One more example for this topic. Let's solve the equation. X squared y prime equals to 3xy plus e to the x y squared. And we have the restriction on the independent variable x positive. Again, this condition we have seen earlier, it is the restriction on the independent variable. It helps that when we have natural log absolute value of x, we can ignore the absolute value. But it's also said that, well, if our independent variable x here represents time, then we are interested in future time, not in the past. There is no initial condition for this problem. So as usual, when solving first order differential equation, we should divide both sides by the coefficients in front of y prime to make y prime by itself. Divide. So we divide through by x squared. We get 3xy divided by x squared e to the x y squared divided by x squared. And simplify that. Where y prime equal to, simplify and we write the coefficient separately. So 3x divided by x squared, we have 3 over x, and separate y, and then e to the x over x squared, and separate that y squared. And rewrite into the format, we have y prime minus 3 over x, y, and then e to the x over x squared, y squared. And this matches linear equation. Bernoulli equation. The left-hand side looks like linear equation, but because the right-hand side we have the coefficient times y squared, that Bernoulli equation. So let me write here. This is y prime plus bx y equal to cx times y to the n. That's the format for Bernoulli equation. So how do we solve this Bernoulli equation? What is the first step to do? You may pause the video and try to do yourself. And what we do first is to try to get of y squared. So we're going to multiply through by y to the negative 2. Multiply through y to the negative 2. So then we have on the left hand side y to the negative 2 times y prime. And then let me rewrite the coefficient first, minus 3 over x. And then we have y to the negative 2 times y equals e to the x over x squared. So y to the negative 2 times y prime minus 3 over x. Simplify the middle part here. We get y to the negative 1. And then on the right hand side, e to the x over x squared. Now we introduce new unknown. V equal to whatever power of y we have in the previous step. which is y to the -1. And then we compute the derivative dv dx using the chain rule. dv dx is dv dy times dy dx. And v is y to the -1, so dv dy is minus, using the power rule, minus y to the -2, and dy dx is y prime. So we have the factor of y to -2 y prime, which appear in the differential equation earlier, but there's a minus in front. Let's get rid of that by divide by multiply through by -1. So we will have minus dv dx equal to y to the -2 y prime. And now we will need to substitute into equation. Substitute into equation. So how do we do that? Whenever we see y to the -2 y prime, we should replace by minus dv dx. And that's exactly right here. So for this, we have minus dv dx. And then whenever we have y to the -1, we should replace by v. Let me make blue. Y to the -1, we should replace by v here. So rewriting the equation, get minus dv dx and minus, I believe, 2 over x, that's the coefficient, sorry, 3 over x. And then y to the -1 up here, which is v. And on the right hand side, we have e to the x over x squared. As before, we have a new equation, linear equation, linear with the unknown v, but it's not in standard form yet. It's not standard form yet because we have minus of dv dx. We need to turn the coefficient here to 1. So we could say multiply through by -1. Then we turn it into v dx plus 3 over x v equal to minus e to the x over x squared. Now it's in standard form. What px is 3 over x and qx minus e to the x over x squared. As before, we need to find integrating factor. Mu of x and solve for v. And after having v, we will go back and solve for y. Again, you may pause the video and try yourself this. But the integrating factor is e to the integral of 3 over x dx. So we get e to the 3 log of absolute value of x. No adding c here. And because x is positive, we can ignore the absolute value. And we need to simplify the integrating factor. We did this before. in the property of logarithm, we need to bring the exponent in. We have e to the log of x cubed. And now we can cancel e and log to get x cubed. This is the integrating factor. Now we multiply standard form by x cubed. Standard form that I am referring to is here, and we need to multiply through by x cubed. So each term must be multiplied by x cubed. So on the left, we have x cubed dv dx plus x cubed, and then 3 over x v. On the right, we have minus e to the x over x squared, and then we multiply by x cubed. Now, the left hand side, you don't need to simplify it. We know already that this must be the derivative of product v times x cubed. We should check what is always true if we do correctly. And then here we simplify this. We have minus e to the x times x. I integrate v x cubed integral of minus e to the x times x dx. How do we do this integration? Minus integral of minus e to the x times x dx. Yes, you need to use integration by part. u dv equals the integral of, let me recall that integral of u dv is uv minus integral v du. Now, not to confuse the v here with the unknown v that we have over there. So let me denote this by u1 v1 is u1 1 minus integral of v1 du1. So not to confuse with the unknown v that we are solving for. For this integration by parts, exponential times polynomial, the u, which is u1 in this case, will be x. And the dv, I will take the exponential, so minus e to the x dx. And then d of u1 is just dx. So the v1 will be the integral of minus e to the x dx. We will get minus e to the x. And so integral of minus e to the x times x dx will be u1 v1. u1 here and v1 there. Multiply together. We get minus x e to the x minus the integral of v1 du1. v1 is minus is du1 is just dx. And we get minus x e to the x, and minus become plus integral of e to the x dx. But integral of e to the x is the same, e to x, but don't forget to add c right here at the step when we do the integration. That is the assigned step to compute in the integral of the right hand side. Now rewrite it. we have v x cubed equal to the integral, which is minus x e to the x plus e to x plus c. But what is v? What is v? What is the relation between v and the unknown y? V, if you remember, we put v to be y to the negative 1 right there, or the same as 1 over y. So we may replace v by 1 over y, then we get 1 over y x cubed equal to minus x e to the x plus e to the x plus c. Now try to solve for y. We could do, we divide everything by x cubed, say like this, minus x e to the x plus e to the x plus c divided by x cubed, and solve for y by taking reciprocal, by flipping this. We get x cubed divided by minus x e to the x plus e to the x plus c. And this is the general solution. Why is it the general solution? Because it has a constant c. We don't have any initial condition to solve a c. Now, before we conclude, we need to note one more thing that I didn't specify at the beginning, that how do we solve this equation? We need to multiply through by y to the negative 1, right? Sorry, by multiply through by negative 2. But in order to do so, we need to assume that y is not 0. Otherwise, we are doing division by 0. That's not allowed. We're assuming y different from 0. Now, if the initial condition already says so, then it's okay. Initial condition give us what the value of y is at say x equals 0, or at other values of x. If it says y different from 0, then it's okay. But here we don't have initial condition. We need to be careful. So know that what happens if y equals 0, then we cannot divide. But it turns out when y equals 0, it satisfies the differential equation, satisfy the ODE. So it is we saw this in the previous topic, it's a constant solution. Now let's see why y equals 0 satisfy the differential equation. Go back to the very beginning. This is a differential equation. When y equals 0, the derivative of constant is 0. So whatever x squared is, x squared times 0 will be 0. On the right hand side, whatever x is, 3x times 0 is also 0. And then e to the x times 0 is also 0. So y equals 0 satisfies the equation, meaning that it is a solution. So let's write out the conclusion. We have two things. Y equals 0 is a constant solution. That's the first. And then the general format, y equal to above here x cubed divided by minus x e to the x plus e to the x plus c is the general solution. And this is the end of the lecture for today.